Hello students, this is Sintham Patel and welcome back to the video lecture series of the fundamentals of machine design. In this video you are looking at the notes of the chapter number 1. This is actually the part 2 of the notes. Part 1 of the notes was already covered in the previous video. If you want, the link of that particular video will be provided in the description of this video. Also, right now you are seeing the PDF or the handwritten notes of the chapter number 1 on your screen, and the PDF is also available in the description of the video, so that you can download from the link available in that particular description. Right now we are talking about the part 2 of the chapter number 1 notes. As I have covered part 1 and it was getting lengthy a bit, that's why I cut that video off and made another one for you guys. And that's why I hope this all the concepts will help you to get the better results in from the question asked in the chapter number 1. So chapter number 1 consist of the 3 different basic topics. The first one was simple stress and the strain, which was already covered in a part 1. In today's video, we are going to look at the thermal stress, and if the time permits us, then we will also cover the topic number 3, that is the elastic constants. So you are looking at the thermal stress topic. The thermal stress topics concepts are already shown in the previous videos. So some of the concepts are already been explained very well, and we are going to look at the different examples which were not covered in the previous video. So I also included those examples in this note so that you guys don't get confused while solving the example in your examination, and you can solve it like a familiar example. Okay, so basically this video contains all the topics which were already covered and not covered, so pay attention a little bit more. We will go through a bit quickly for the topics which were already covered, and we will pay attention a bit more for the topics which are new for you guys. And let's get started with the first one, that is the definition of the thermal stress. So the definition of the thermal stress is already pretty clear from the previous video. If you haven't seen it, then you go through my playlist and have a look at it. Then the thermal stress is defined, or it is the with the increase in the temperature. Okay, so basically thermal stress is generated with the sum of the basic conditions. So first condition is that the body must have to suffer a change in a temperature. So if there is a change in a temperature, then body will try to expand or contract based on the temperature change. If the temperature is increasing, the body will try to expand, and if the temperature is reducing, then the body will try to contract. So based on the temperature change, if you prevent that free expansion or contraction, then the body will resist, because the body wants to expand or contract based on the temperature. Okay, and you are not allowing the body to do so, and that's why if you provide the constraint, if you provide the restriction on the body, then the body will resist, and due to that resistance, stresses will be generated, and those stresses are known as the thermal stress. We already know that type of terms and the concepts, so we will go through quickly. We will not waste much more time. We also know that the delta L due to the change in the temperature or due to thermal stress can be calculated using the equation that is nothing but the L alpha delta T, which is represented over here. So L alpha delta T is the equation of the change in length due to the change in temperature. Now what is delta T? Delta T is of course the change in a temperature. What is alpha? Alpha is the coefficient of temperature, or coefficient of constant which is dependent on the temperature change. Okay, so coefficient of thermal expansion basically. L is the original length of the body, and if the body is facing some temperature change, the delta L will be the change in the length. Okay, so this is the equation of the delta L. L, alpha, delta T, each and every terms are explained over here. The thermal stress requires 2 different conditions, and both the conditions I just already covered. That is, there should be a temperature difference and there should be a resistance to the deformation due to temperature difference. So if one of that condition is not satisfying, that if one of these conditions are not satisfying, then the body will not suffer the thermal stress. So this both conditions should be satisfied in order to generate or calculate the thermal stresses into the body. Okay, if the expansion due to the increase in the length is to be prevented, then the external compressive load is required, which produces the compressive stress. And if the temperature of the bar is decreased and contraction is prevented, then the tensile stress will be produced. That is but obvious thing. If body tries to expand and if you restrict it, then the body will try to resist that, and due to the resistance, to contain that resistance, the stresses generated will be compressive. The nature of the stresses will be compressive, because body will try to expand and you are not allowing the body to expand, and that's why the stresses generated due to the thermal condition, this thermal condition will be of the compressive nature. And if the body is trying to contract, if the body's length is trying to decrease and you are not allowing it to decrease, then the body will try to decrease itself, but you are not allowing. That's why the stresses generated will be of the tensile nature. So this is very common sense and very easy topic. Now we will look at the thermal strain, which was already covered in our video. That is nothing but the delta L upon L. We know the equation of the delta L, that is L alpha delta T. If you cancel out the L from the denominator and the denominator, you will get the value of the thermal strain, that is epsilon. TH in the suffix can be easy to identify whether it is a thermal or not. So epsilon equals to alpha delta T. That is our final equation of the thermal strain. So that was the case of the thermal strain. Now we will look at the different cases. There are 3 different cases which you may be asked by the GTU, and examples must be solved based on those cases. So the first case is pretty simple. The first one is the deformation is permitted or free expansion. So you are not restricting your body to either side, whether if the body is trying to expand or contract, you are allowing the body to do so. Why is that? Because you have not provided any restriction or the constraint. So if you are not providing any restriction, there will be the change in the length, there will be the deformation, but there will be no stress generated into the body, because the second condition, that is if the free expansion or contraction is prevented, is not satisfied. We are not preventing here any expansion or the contraction, and that is why the second condition fails. That's why your thermal stress answer over this case is 0. Although there is a deformation, so there might be the question asked in your examination that what will be the deformation for the particular body. So you just don't have to write answer 0, because the stress is 0, deformation is not 0. So in this particular case, you will have to remember that the deformation will be there, but this deformation is natural. There is no restriction or the constraint over the body, and that's why the body will not resist. Without the resistance, there will be no stresses generated into the body. So that is the case 1. Now case number 2. Case number 2 is the case where a deformation is prevented completely. As you can see in this diagram, the body is completely restricted between these 2 restrictions. So these are the 2 restrictions within which the body cannot move. Okay, and if you are changing the temperature, if you are applying the delta T temperature change, then the body will try to either expand or contract based on the change in temperature. Okay, so let's say we are increasing the temperature, the body will try to increase the length of it, but you are not allowing the body to expand, and that's why that will create the stress in the body. Now in order to calculate the stress in the body, you just have to imagine one condition. In all the example, we are going to do that one thing, that we will assume that the body is free to expand. Okay, so first of all, that is not the case over here. Okay, the body is completely restricted, but still we are assuming, I am using the word we are assuming, that the body is free to expand. If the body is free to expand, then it would expand something like that. Okay, something like this. This is the expansion that could have happened if the body was allowed to expand. But you have prevented the expansion, and that is why the prevention requires some amount of the external agent which will push the body, which will keep pushing the body to its original condition. So in order to push the body, you will have to apply an external force. Now this external force will be generated by the restriction that you have provided. Consider yourself pushing on the wall is pushing back towards you. Similarly, the body is pushing towards the restriction and the restriction is pushing back on towards the body. Okay, so the reaction generated by the restriction is represented by R, and this R is the resistance, and this resistance will cause the thermal stress, and that is why we are going to put the value of this R as the force in our equation. So if you want to find out the delta TH or delta LTH, both are the same, then we will use our basic equation, that is PL upon A, and instead of the P we are using the R. Okay, so R is over here. So we can use plus for the tensile and minus for the compression, so that we can get the answer plus or minus. If the answer comes out to be the plus, then the delta answer is plus, it indicates that your length is increasing, and if your delta answer is minus, then it indicates that the length is decreasing. Although the length is not increasing actually, because we have restricted your length. Okay, so if your body was allowed to move freely, then and then it would have expanded like this, but it is not allowed. That's why we can say that it was compressed this much. So this is the change in length which was compressed by the restriction. So we can say that this length is compressed, and that's why the nature of the thermal stress over here is the compression. So this much length should be compressed in order to keep the body in its original length. So now we will move on to our last case, and the last case is nothing but this one. So in the previous case, the equations which were left before are like this. The delta TH for the case number 2, it was L alpha delta T, which can be plus, which can be minus based on the condition. If you want to find out the strain, then you can find out the strain by alpha delta T by delta L upon L. That is the basic equation of the strain. And if you want to find out the stress from this equation, then we know the relation between the sigma and the epsilon. You just have to multiply E with the epsilon. So if you multiply E in this equation, then you will get the answer of the stress. So this is the basic equations for the case number 2, which is widely asked in your GTU examples. Now case number 3 is also a very pretty good topic to be asked in your examination, so you should pay attention over this here also. The case number 3 is the deformation is prevented partially. So the deformation is not completely prevented, it is prevented partially. What does that mean? So this is the original figure. This is the original figure where the body is restricted on this one side, but on the other side there is some gap over here. There is some gap over here, and that gap is represented or denoted by the lambda like this. So this is lambda, which is also known as the yield. You must understand this word yield. This is also known as a yield because it will be used in your examination. Okay, this is also known as a yield or a lambda. Okay, so yield or lambda both are the same. So what can happen over here, that the body, if you increase the temperature, okay, if you apply delta T, if you are increasing the temperature of the body will try to expand, but up to this point, the body will not face any resistance because it is moving freely. Okay, up to this point, within the gap the body is expanding freely, and for free expansion there is no thermal stress. So we must not calculate the thermal stress for particular that free expansion. So what are we intended? So we need to find out the total thermal deformation that could happen if the body is allowed to freely expand. So let's say this much body would have expanded this much delta TH. The body would have expanded this much if the body was allowed to expand freely. Okay, but the body was not allowed to expand freely. The body was allowed to expand freely, but up to this point only. So this much amount of the deformation was prevented. So we need to calculate the thermal stress only for this much amount of the thermal stress prevention, and that was represented by delta A, and delta A is the reason because of which we are facing the thermal stress into the body. Okay, so this is the main reason which you need to consider, and that is why we have calculated delta A over here. Delta A can be calculated by delta Th minus lambda. That is very basic arithmetic operation. And if you want to find out the delta A is prevented because of R. R is the reason because of the delta A. Okay, and that is why it can be calculated using the PL upon AE equation, that is RL upon AE. If you put the value into this equation of the sigma TH, then this equation will give you the answer like that, that the PL upon AE or the delta L by L into E. Again, this basic equation, sigma equals to epsilon into E. Instead of the epsilon, we have written this bracket. So instead of the epsilon, we have written this bracket, that is nothing but the delta L upon L, and instead of the delta L, we have written delta Th minus lambda. Okay, so if you put the value of delta Th, that is nothing but the L alpha delta T from the previous case, because delta Th is the case of the free expansion, and for free expansion you can write this equation, that is L alpha delta T minus lambda upon L. So this was the case of the case number 3. If you simplify this case, then you will get the answer of the sigma Th as this. This is your final answer for the sigma Th. If you know this answer and if you can remember this answer, then you will be able to solve the example very easily. You will not have to derive at the equation at a time. So I suggest you guys to remember this equation so that you can easily solve the example. So the next case is the thermal stresses in the bar of the varying cross section. Now this is the case where the bar of the varying cross section, this is something like the compound bar. Okay, so this is something like a compound bar. Okay, where the cross section of the two bar are different. Okay, compound bar. Okay, for this type of a bar, there has been two different steps to solve this type of examples. To solve this type of a example of a thermal stress, you need to follow two different steps. The first step is this one, that let's say this is the bar number 1, okay, and this is the bar number 2. Okay, so if the bar 1, and now what are we going to do is we are going to increase the temperature of both. Whatever we are going to do is change in a temperature. Okay, so that whatever the change in a temperature is for the bar 1, similar the change in a temperature will be for the bar 2, because both are connected. So change in temperature for both the bar will be the same. So either they will expand, they will try to expand, either they will try to contract. So this is the basic condition which you need to remember. So let's say for one example, we are increasing the temperature. So bars will try to expand, but bars cannot move beyond this limit, because we have restricted the bars on these two particular points, point A and point C. So what will happen? This bar will try to this bar will try to expand, and this in this direction, and this bar will try to expand in this direction. So both will try to compress each other. Okay, so let's say one bar is trying to move over here and another bar is trying to move in the opposite direction. So both the bars will try to push each other, and that is why the force which is applied by the one bar over the other will be the same by the for the one bar for the another bar over the first one. So let's say the force applied by the one bar is P1 and force applied by the another bar is P2. So these two forces are the same, and that is why if we use this relation, that is stress equals to force upon area, then you can directly write P instead of P1 sigma 1 A1 and instead of P2 sigma 2 A2. So this is our first equation which you are going to use to solve this example. The first step to solve this type of example is this one. Okay, the second step is delta L. Now as you can see, the bars are completely prevented, so there will not be any amount of the deformation, actual deformation. But what are we going to do in this case? Again, we are going to assume that if those bars are allowed to expand freely, then how much expansion would have happened? Okay, so we are assuming that these bars are free to expand. And that expansion, let's say delta L for bar 1 and delta L2 for bar 2. This was the free expansion, but it is not happening in this case because the expansion was prevented by the restriction, and that is the reason for your stress. So although this expansion has not occurred, but still this expansion has prevented due to the application of the restriction, and those restrictions are the reason for the compressive force, and that is why this expansion is prevented, and we must consider this prevented expansion as the reason for the thermal stress. Okay, so let's say the bar would have expanded up to this, second bar would have up to this, so overall expansion must be equals to summation of both the expansion. So this is our second step which you need to remember, but what we are going to do, we are going to convert this second step in terms of the stress. We know that delta L is nothing but the PL upon AE, but from this equation P by A can be considered as sigma, and that sigma is written over here, and the rest of the L by E is written as it is. Okay, so basically these are the two equations. This was the first one and this was the second one. So two equations using which we will be able to solve any example. You will be able to solve any example of the compound bar. Okay, compound bar basically. Similarly, what are we going to do next is the calculation of the thermal stress in the composite bar. So this is the composite bar. We all know that because we have seen the examples based on the composite bar in the previous notes. So composite bar basically is the bar which is made up of the two different materials, and both the materials are connected to each other rigidly. So they cannot move separately. They must move together. Okay, so if there is a change in a dimension, the change in dimension for both the material will be the same. So that is the basic idea of the composite bar. But let's say we are assuming over here. Okay, so let's say we are assuming that both the materials are different. So some material or one material may expand more for the change in a temperature, and another material may expand a little less for the change in temperature. Okay, for example, a metal would expand more as compared to wood. Okay, as compared to wood or rubber, a metal would expand more comparatively. Okay, that is the very well known fact, and the same fact is applied over here. Let's say this is a copper. The copper is having the higher coefficient of thermal expansion, that is alpha. Copper has higher value of alpha. Alpha for copper is higher. Okay, and alpha for steel is lesser. Okay, so this is the reason, and that is why the copper would try to expand more as compared to steel. So we are assuming that the free expansion is happening. These two materials are not connected to each other. We are assuming that, but it is, in real condition it is not possible because both the materials are connected to each other. So this type of expansion cannot be possible. Okay, is not possible. So what will happen? The copper is trying to expand more as compared to steel. So copper will pull the steel in this direction, and steel will pull the copper in this direction. So both the material will try to pull and push each other so that they can expand in the compromised level. Let's say this is the compromised level. So this is the point at which the both material will end up expanding together. Okay, so the copper will so if this is the case, if this is the final expansion, then we can say that the copper is compressed this much. So copper is compressed this much and steel is elongated this much. So this is the elongation of the steel and this is the elongation of the copper. Now this elongation and compression of the both material will produce the stresses in those material. Although the forces applied on each other are the same, but still the stress value for both the material might be the different. How to calculate those stress value? There are another two steps to calculate this type of a stress value. What will be that? What will be those steps? First one is the same. First one is this one, that is the force applied for the copper on the copper is equals to force applied on the steel. So if you convert those forces into the stress, you can get these equations. Now the second step. Second step is pretty much simple, but if you use your common sense then you will be able to understand it, otherwise you will not understand it. First of all, let's say this is our final condition. This is the final condition at which both the materials are being elongated. So the total strain of the copper is this much. Okay, so this is total strain of copper. This is strain of the steel, but we need to calculate the strain of the steel by which is resisting. So let's say this is the strain of the steel. Okay, so this is the epsilon, and we need to, if you want to calculate the value of this alpha Cu into delta T, then you can directly relate this much amount of a compression, and that compression is represented by the epsilon. So if you want to calculate the final strain which is generating the stress, then you can directly cut out the value from the alpha Cu minus epsilon. Similarly, if you go for the another one, for the steel, you may write it epsilon minus alpha steel into delta T. And if you sum up both these values, let's say this one and this one, if you sum up both this value, then you will simplify this answer, and by taking the delta T as a common, you will get the answer as this one. So this is our final answer. So this is our second step. So whenever a composite bar example is asked for the thermal stress calculation, you will use two different steps. The first one, the force P for first material is equals to force P for the second material, and the second step is strain for the first material plus strain for the second material is equals to change in temperature into alpha, that is the coefficient of thermal expansion of the first material minus coefficient of expansion of the second material. Now which material should be used over here and which material should be used over here? There is one little trick over here. You can easily remember it that you must subtract the smaller value alpha from the larger value alpha. So whichever the value of the alpha is given for both the material, you just have to compare both the values, subtract the smaller value from the larger value. So this answer will always be positive. Okay, and it will be multiplied with the delta, and this will give you the answer of the epsilon plus epsilon steel. Using which these two strains, we are going to convert it in terms of the stresses, and we are going to find whatever the asked in your examination. So let's get started with the example so that you will have the clear idea about it, and we will see the application of those concepts which are written over here in our example, so that you don't get confused about it. First example is, as you can see, very simple example, that is a steel rail is 10 meter long and is laid at a temperature of 20 degrees centigrade. So 20 degrees centigrade is the original temperature. The maximum temperature is expected is 50 degree. So the temperature may increase up to 50 degree. So what will be the delta T? Delta T will be 50 minus 20, that is 30. Estimate the minimum gap between the two rails to be left so that the temperature stress do not develop. So if you might have noticed that the railway tracks is having some amount of the gap between the two rails. Okay, and how much gap should be provided in order to prevent the thermal stress into those rails is to be calculated from this data. So the coefficient of linear expansion for the steel is 12 into 10 raised to minus 6. Okay, per unit length. Okay, basically this is the unit of the alpha. Coefficient of linear expansion is the coefficient of thermal expansion, both are the same. So L is given as a 10 meter, which can be converted into mm like a 10,000 mm. Delta T is 30 degree and alpha is 12 to 10 raised to minus 6 per degree centigrade. So they are trying to find out the gap which is safe for the safe to prevent the thermal stress. The thermal stress will not be generated if it is not prevented. So if there is sufficient gap between two rails that it can freely expand, then the thermal stresses will not be generated. So for free expansion, we have the equation of delta L, that is L alpha delta T, and if we have the value of L alpha, delta T. Put those value in this equation and calculate using the calculator. You will get the answer as a delta L, that is 3.6 mm. So this was the end of this example. Now we will move on to another example, and that is the steel bar ABC having 25 mm diameter. So ABC bar, as you can see in this diagram, ABC bar is having the two different steps over here. And the first step is this one. AB is having the diameter of the 25 and 16 mm diameter of the BC. So BC is having the diameter 16. So both the dimensions are written in this diagram. Is rigidly held between the two supports A and C. So as you can see, the expansion or contraction is completely prevented. This is the case number 2. Now, if the temperature is raised by 30 degrees centigrade, now temperature is already raised, they have not provided you the initial and the final temperature. This is the raise in the temperature, that means they have directly provided you the delta T. So delta T is given as a 30 degree. Determine the stress developed in the part AB and part BC. So you need to calculate the stress in the part AB, that is the first part. Let's say the stress generated over here is the sigma 1, and let's say the stress generated over here is the sigma 2. So you need to calculate sigma 1 and sigma 2. Take the E or Young's modulus as a 200 gigapascal and alpha as a 12 into 10 raised to minus 6 per degree centigrade. So alpha is provided, E is provided. The first step, first and foremost for the compound bar is this one. That is, the force applied by the one bar is equals to force applied by the another bar. Action and reaction equal and opposite. So sigma 1 A1 equals to sigma 2 A2. So sigma 1 A1 can be calculated from the diameter of the first part. As the diameter is provided, we are assuming that its cross section area will be circular. So for circle, we can use the equation pi by 4 d square. Diameter d is provided as a 25. Similarly, A2 can be calculated as a pi by 4 d2 square, that is 16 square. So both the area value is provided, and if you cross multiply this area and simplify the answer, then you can find this relation between sigma 1 and sigma 2. That will be our equation number 1. Okay, so this is our equation number 1. Now we are going to move forward for the second case. The second case itself was like this. This was our second case. So we assume that I have clearly written over here. We assume that the free expansion is happening in this particular case. So if the free expansion is happening, the bar 1 would expand delta L1, that is L1 alpha delta T, that is 0.18 mm, and bar 2 would expand for 0.126 mm. So this was the case of the free expansion. So total expansion for both the bar, would be delta L equals to delta L1 plus delta L2, that is 0.306 mm. That was the case of the total expansion. Now we will apply our equation, second equation. Second equation was this. Delta L, that is total expansion. Total expansion is equal in terms of the delta L1, that is written like this, and delta L2 is written like this. So this is nothing but the delta L1 and delta L2, which can be converted in terms of the stresses and written like this. Okay, so L1 is known. E for both the bar is the same, because they have not mentioned that the bars are made up of the two different materials. So we are assuming that the material for both the bar is the same. So E for both the bar is given as the same. So E is provided. And as you can see, if you put the value of L1 and L2, there is only one value remaining, that is sigma 1 and sigma 2, which is unknown. But from the equation 1, you can put the value of sigma 1 as 0.409 sigma 2. This is the value of sigma 1. So if you look carefully in this equation, then there is only one unknown, that is sigma 2. Take out common from this equation and make it as a subject and simplify the equation. Then you will get the answer of sigma 2 as 110.38 Newton per mm square. So this is the answer for the sigma 2. From sigma 2 you can calculate the sigma 1 using the equation number 1, and we will get our second answer. So this was the case of the compound bar where the thermal expansion is prevented completely. Now we will see another example where we will see a composite bar. Okay, so basically a composite bar example. A composite bar example is like this. Okay, as you can see from the data itself indicates that a steel rod of 25 mm in diameter is inserted inside the brass tube. So outer material is the brass tube and inner material is the steel rod. The brass tube of 25 mm internal diameter and 35 mm external diameter. So brass tube is having the 25 mm internal diameter, and that is why, as you can see, there will be no gap between two materials, and that's why we assume that both the materials are connected over there or at the ends. The ends are rigidly connected together. So ends are connected, that's why we can consider it as a composite material. The assembly is heated by 30 degree. So whatever the temperature right now, it is heated 30 degree more. So 30 degree is the change in a temperature. So delta T is directly provided. So we don't have to find out the original temperature. They have already given the delta T value. So don't have to worry about the original temperature. Find the value and the nature of the stress developed in the both material. So this is the question which you need to carefully aware about, that you are being asked about the calculation of the stresses and the nature of the stresses for both the material. For both the material, Young's modulus is provided, and coefficient of expansion is also provided. So now our first step must be the first one, that is the force for the force applied by the one material will be equals to force applied by the another one. So that is our first step, and the second step we have already discussed in the previous notes, that epsilon for the first material, epsilon for the second material summation is equals to delta T into alpha of one material, larger material or the larger alpha minus smaller alpha. Okay, so we are going to do that particularly in this case. Let's see further. As the diameters of both the material is provided, you can directly calculate the value of the steel and brass using those equations. We know the method. We are not going to repeat those methods. We have the answers over here. Alpha for brass is greater than the alpha for steel. So brass material will be compressed and steel material will be elongated. That is the basic nature or the basic sense which you need to remember. Okay, so the larger alpha material will be compressed and the lower alpha material will be elongated. That you need to remember. So the larger alpha is brass tube. Brass tube will be having a compressive force and steel rod will be having the tensile force. So whatever you are going to do is the first one. The first step is this one. The first force for the steel is equals to force for the copper or the brass, and if you write the force in terms of the stress, you can write it like this. Put the values of the area and cross multiply it and simplify it, then you will get this equation. This is our equation number 1. Okay, now we will move over to our second step, and the second step is this one. Second step is this one, where you will see the strain for the first material brass and the second material, that is steel, equals to delta T plus larger alpha minus lower alpha, smaller alpha. So if you convert this strain in terms of the stress, we know that epsilon equals to sigma upon E, and this relation is used over here to convert in terms of the stress. So we need to calculate the stress, that is why we are converting everything into the stresses. So sigma B and sigma S. From the equation number 1, we are going to convert this in terms of the sigma B, and now in this equation the only unknown remaining is sigma B. If you take sigma B as a subject and calculate the rest of the value, then you will get the answer of the sigma B as the 10.40, that is 10.40. Okay, so that is the answer of the sigma B. Similarly, for sigma S, you can directly calculate the answer from the equation number 1, and sigma S answer will be calculated like this. So this was the basic examples which you need to remember, which you need to practice. Practice those examples from the question bank, practice those examples from my notes, and link to download this node is available in the description. Go check out that description and download the node so that you can have a clear idea about the chapter. The third part of this note will be covered in the next video, as this video is becoming lengthy. So we conclude our lecture over here. Thank you.